Thank you very much for this opportunity to speak about this. Well, especially I would like to mention that the very beginning of this story, I had an opportunity to speak in the front of Professor Durham 15 years ago, and this is just will be clear what sort of progress actually appeared now in this topic. So I'm speaking about local analog of Grothendieck's conjecture, and especially about its one-dimensional case. So this means that I'm going to work with local fields, with complete discrete valuation fields, which have a finite residue field of characteristic P. And okay, just to make more precise the terminology, global Grothendieck conjecture. So in this setting is the following: if we have algebraic number field, then the knowledge of E is equivalent to the knowledge of its Galois group. Well, just trying to speak in the simplest possible terms about this. And if K is a complete discrete variation field with finite residue field of characteristic P, well, K, in this case, we have arrow only in one direction. If you know K, then you know gamma K, and unfortunately this very, very weak invariant well, and complete description of all possible groups. So that was done by Janssen and Wingberg. And here, in our situation, in the case of global fields, this is very strong invariant. Okay, and in order to save this situation, the idea was just to take K and attach to this the whole Galois group and its ramification filtration by ramification subgroups in upper numbering. And so we have a group, and we have a decreasing filtration of normal subgroups, and this is just more complicated object. And local analog of Grothendieck conjecture in one-dimensional case, it gives an assertion that in this case one can recover the structure of field K from this group theoretic data. Well, just to remind very briefly, these ramification subgroups, well, so they actually never appeared during all these days. Just very brief idea. Ramification subgroups gamma K V. They are defined for all rational numbers V, positive rational numbers V, and come from the following very natural arithmetic idea. If you have a finite extension, finite Galois, in this case, we can organize on the Galois group of this finite field extension filtration for any, just again, rational number Q. We define this as the set of elements in Galois group such that if we take normalized valuation VL, act via gamma on uniformizing element, and then if we have that this is greater or equal that n of x, then we just consider this subset of the whole Galois group, and this will be called the ramification subgroup in lower numberings, where n of x is the following n of x is natural number such that x is between this and this. Well, and then just in order to pass to all finite extensions, we need to introduce upper numbering. So it's given via Erbrand function. X goes to v, and this Erbrand function is defined by conditions. It goes through 0, 0, and its derivative is index in of this subgroup this way, and this is piecewise linear function. And actually, don't think about this v as something, okay, what just must have interpretation. Actually, this means that there is some correction for this x, just another scale. And then in these terms, in terms of these upper numbers, we have very nice behavior of gamma L K V, what is by definition gamma L K X. Well, and then just with respect to all finite extensions, and then we can say just let its inverse limit gamma L of K V for all L. Well, so this is very nice arithmetically motivated additional structure on the whole Galois group of this complete discrete evaluation field. It really reflects arithmetic, and say, for example, maximal unramified extension is a subset of points just fixed by the first ramification subgroup with upper index 0. If you consider tamely ramified extension, this must be k bar gamma k, and it's usually denoted by 0 plus, where this is just the closure of the union of all subgroups where v is positive. So this means that the next information what comes actually here, this gives us already information about next step here. And then also the structure is very, very rich. So because actually any rational number positive appears as a break of this filtration. So this means that all of them are different. Say if you take even very, very close rational numbers, then just because of this inverse limit, so they are different, and this is really very, very rich structure. Okay, and what I mean, say here by this statement, and well, at that time, 15 years ago, so that was just a hope that something like this is happening, and we have the following results in the moment. First of all, Moshitsuki actually, that was a special application of his general methods, what he applied to prove global cases of Grothendieck conjecture. In very elegant paper in '97, he proved this local conjecture in the case when K is just finite extension of periodic field QP. So this means that characteristic zero case of this conjecture, it was proved here, and this is really very elegant application of Hodge-Tate theory, of periodic Hodge-Tate theory. Well, but no chances to generalize this to the case of fields of characteristic P, and especially just even to think about high-dimensional local fields from this point of view, actually that wasn't possible. I also just discovered here, I remember that that remark of Professor Delin, what he did, say just, if we manage to prove this, then okay, if it's sort of non-explicit stuff, if just still any information, any explicit information about ramification filtration still is used in some non-explicit way. So just mean, if this statement does not give us some explicit ideas about the structure of this filtration, so he called this a sort of religion. Just will appear another religion, and say, and after this, what one should think again, just what it means and all that. And this appears actually as that sort of religion. Well, and just independently, so it appeared in 2000. So I proved this in the case where characteristic of K, just what is P, is not 2. This means that actually characteristic of K, it could be 0 or P. And this was actually application of explicit description of this ramification filtration for fields of characteristic P modular subgroup of commutators of order P. Maybe I will write it. So application of explicit description of subgroup modular subgroup of commutators of order P if characteristic of K is P. And after this, so because in this case actually that was possible to study this filtration, just explicitly given generators of this, and actually we needed only the case gamma K of V modular C3. So because if you know this filtration modular subgroup of second commutators, this means that it's given just by class field theory and nothing special actually just happening in this case. Well, but if we consider this modular C3, just in terminology of Florian, central by nilpotent bicentral, well, abelian bicentral extension. So in this case, really, we have definitely non-trivial information about this filtration, and that was possible just to use these explicitly given generators and to analyze automorphisms of such groups which respect this ramification filtration, and that gave really very serious restrictions for these automorphisms, and actually that was possible to prove that all of them are coming from analytic automorphisms of this field of characteristic P. Well, and this explains why I have here restriction that P is not 2. So, and also this restriction actually comes from the following fact. When describing these ramification subgroups, we need somehow to go to switch to Lie algebras. And after this, so because it's just quite natural, it's coming extension of scalars of those with Lie algebras. And if we are in the situation of nilpotence class less than P, then we have equivalence of categories of P groups and Lie algebras, and this is actually justified. Well, but okay, if P is 2 and we need to proceed modular third commutators, in this case we are not able to use these advantages. Well, and after this, the case of characteristic 0, that was just done by application of the field of norms functor. So because essential part, again, it has interpretation in terms of field of characteristic P, and then one can just finish these arguments. Well, and next progress actually was, And also, in this paper, I have sort of effective version of this proof. So what means that, okay, under some assumptions, we are able to use only finite segment of this filtration, and this also has relation it also has a direct relation with with some paper of the Lin. I'm going to explain this later. Okay, next progress appeared in 07. So this is where I was able to establish the same fact for high-dimensional local fields, which come from those partial chains what Florian used in his talks. So this is the case of high local fields. And this is also so because in this case, several new ideas actually would be required. So because even to construct theory of ramification subgroups in this case, and that was a new result. Well, and after this, some additional structures also play very important role here. Say we must treat in this case Galois groups which are provided with some another topology, not profinite topology. This topology comes from that special topology what one can introduce on high-dimensional local fields. I hope to speak about this maybe at the workshop. Well, yes, yes. And okay, and finally, recently, so there is paper what fortunately passed through very long referee procedure, and so this is actually a modified approach. Well, actually, it's written only for one-dimensional case, but it just goes even for high-dimensional local fields. Well, but at least to finish this in one-dimensional case, and this includes actually the case of P2. And very clearly, it states that all stuff can be made just on the level of Galois groups of maximal P extensions. In the context of Galois group of maximal P extension of K. Well,
just question to 07. Yes, 2007. That is also in characteristic 0, also in characteristic P.
yes, yes.
But then in characteristic 0, you have the first step must be directly from 0 to P. This lexicographical order.
Yeah.
You have the first discrete valuation, so must have characteristic P.
Yes, yes. Yes, precisely. Well, so because only these fields have sufficiently complicated Galois group, otherwise, and all this ramification, filtration, and everything, so it seems they don't play their role. Well, and so just in arithmetic, this is very standard assumption that the first residue field, it must have characteristic P, and then everything is, okay, hard, but it carries some information.
And here you just put the ramification filtration on the maximum quotient.
Yes.
And
Yeah.
that determines
Sorry?
and that determines the field.
Yes, yes, yes. Mm-hmm. The things are that maybe, well, in the case of characteristic P, yes, we have something that up to inseparable extension, say just especially in the case of high local fields. Well, but these are just details, and the situation is such.
In these results which come now new, do you have also a truncated version? So you just have to go modulo in this modulo C3, or maybe
About truncated version, well, since 1998, when I finished this, I forgot about this, and I just discovered this when I printed and started preparing my talk. Oh my God, I have just another truncated version. Well, I hope that arguments are sufficiently general So this means that, well, so yes, it's just okay. So because you really can forget and think that maybe, okay, it's not very interesting. Well, but now I realize that, okay, it's interesting. Well, and yes, yes, and that was developed, and actually it depends on the following structure. Say, if you have two-dimensional local field, in order to introduce its ramification theory, that's what really I need, we must introduce special additional structure. Say, if you have field, say it's two-dimensional, and then you must introduce subfield of one-dimensional constants and subfield, say, of zero-dimensional constants. Okay. Say, in the case of characteristic P, it will be the last residue field, and then it will be field just which is algebraically closed in here and this. And if we replace n-dimensional local fields by these chains, then all theory of high-dimensional local fields just, it seems, it becomes natural, all this ramification indices, AP and all that. And under this assumption, one can introduce here ramification theory, where as upper index we have couples of numbers. Well, and this means that we have again sufficiently dense and rich structure here. So because all other definitions, what say, for example, Said was developing, it has only one number. Well, so and therefore it's sort of just a little bit more poor. Well, but the price you have to pay, this is just to accept this additional structure. But maybe it's also makes some sense.
Is there any comparison between what Saito and Abbes and the node development?
To some extent, yes. So because, well, so
is yours a refinement of that?
It's sort of they have theory, yeah, and they have a lot of questions for this theory. Well, and the thing is that, okay, if I accept that after enlarging this field, I have sort of, well, so actually the role of this field is the following. I will have here, usually, if you consider integers of this chain of fields, then here you have huge singularity, yeah? But then if you go to some extension here, and then you can simplify the singularity, and this will be just sort of semi-stable, sort of in a log of semi-stable reduction. And if you assume that this situation actually occurs here, then both definitions are the same. So this means that they hide these singularities in some procedure. Well, but it's much better if you allow them to just make this extension, and then you don't have this problem, and you have this definition. Well, now maybe some things what I consider interesting. So because just that was done long ago, well, and there was sort of, okay, no relations just with people who are doing global case. Well, so I started thinking just how they can be related. Well, so maybe a couple of words. Interrelation, local Grothendieck conjecture and global Grothendieck conjecture. Say, just take for, okay, E over Q is finite extension. Okay, in this case, E and gamma E, so they determine one another. Take any prime divisor in E, what divides P, consider its completion. So this will play a role of that K. Well, again, so this is just here arrow in one direction, and this is a decomposition group of P. Well, and okay, K and gamma K and this filtration. So this is already right object to consider. Okay, and let's assume, just not trying to think about generality, so because actually it's not essential generality. Suppose E over Q is Galois. So this means that all conjugates are the same. Well, for simplicity, and let's consider the following two properties. I put here star. Some automorphism of gamma EP can be extended to F as automorphism of gamma E. And the following property, Fp is compatible with ramification filtration on gamma EP. Well, and so just looking at global case and local case, I state that they are equivalent. Well, say, for example, if we are in this situation that this F, it comes from some automorphism of algebraic closure of E, well, so, and therefore it induces automorphism of EP, which is compatible with ramification filtration. Say, yes, if we have this, then this Fp, it comes from EP star to EP star. Well, but it contains E, and this just must be mapped to itself because this is given by equations over Q, maybe this. So this means that this field morphism, definitely it just induces this field morphism, and therefore this Fp, it can be extended to this. It looks very strange, so because sort of speculation is that decomposition subgroup, when embedded into the whole group, knows this ramification filtration. Well, so they are sort of not independent. So maybe it's not very strange. Well, so because just thinking about this in the following way, start with finite extension of K. So and it can be realized in extensions of E, where this prime divisor over P splits completely. So this means that if you fix here some extension on the level of decomposition groups, then all complications, they can appear by algebraic number fields where this P completely splits, but so this means that it depends on ramification filtration here somehow. Well, but this also makes it very attractive, just to prove this directly. And why actually this is very, very interesting, maybe the following, again a little bit just non-expected thing. Suppose we are proceeding on the level of maximal P extensions, Fp automorphisms gamma EP on the level of P groups can be extended to F automorphism of gamma E. And the property Fp is compatible with ramification filtration on gamma EP of P. Well, again, what we can say about this? Say, if we have so if we just work in this direction, then it's true again. So because this is true on the level of P groups, and therefore again we have map on the level of completions, and this induces a map on the level of global fields. Well, so this is okay. Well, but what is just about this? And if this is true, then we have analog of that result, of global result, on the level of global fields. But it's not precise. It's not stated in that way. Actually, it must be stated in the following way: P form of global Grothendieck conjecture. Say we can state this in the following way: if F is automorphism gamma E of P, and if it leaves a decomposition subgroup on its place, then F comes from automorphism of EP over E. Well, this is additional thing what is not satisfied, say, automatically, because a field does not contain piece roots of unity, then, okay, it will be just a free group and very simple group. Well, but it's not clear that it must move to itself. Well, but if it's satisfied, and then it's okay. So, and also in the context of P groups, actually what we can, and if the, if this is true, and so and therefore we have its global analog, well, but okay, there are some chances just to prove this. So because in the context of P groups, just that we can use generators and relations, and we can use just successive finite extensions. Well, so in the moment it's a problem. Well, so I'm going to put all my attention. Also, another comment about this P form of global Grothendieck conjecture. Such stuff what so brings me enthusiastic about speaking with people who work in Iwasawa theory. Well, but this is just the thing. If we take gamma E, and then it's just the same as to know E. And suppose, for simplicity again, E over Q is galore. And then if we have this additional assumption, then this is the same as to know classical zeta function of E. Well, now look, gamma E, it determines gamma E of P. If we know gamma E of P, then say if zeta P is in E, then we can recover from this group the structure of maximal P cycloatomic extension. So Galois group E P infinity of 1 over E, and its action on its unramified part and therefore we know its periodic zeta function. My first idea was, okay, so this thing they even called in the same way classical zeta function and periodic zeta function. They must determine one another. Well,
how do you get the cycloatomic quotient?
Sorry?
How do you get the cycloatomic quotient?
Well, so this is just from group theoretic structure. So because if you join roots of unity, then it has purely group theoretic characterization, all disappeared groups. Well, so I can make actually, even in Mochizuki paper, he's doing this. If you know the structure of Galois group, then you can recover how many roots of unity this field contains. Well, so, and therefore, we can recover this part. Well, and this unramified part also has purely just characterization in terms of group structures. well, say for example, if you consider Galois group of maximal p extension, just that Demyshkin's result. Its structure, its relation, it depends how many p power roots we have in this field. Okay, so we have usual zeta function and this, and suppose that the knowledge of p-adic zeta function gives us classical zeta function. So this means that I can come back and I can recover field D from this. Well, but this is sort of, it depends on the main conjecture of Iwasawa theory. Okay, field is not totally real, then okay, this results about p-adic extrapolation again sort of, well, so, but okay, anyway, it looks like the question how they are related. Is it true that one determines another? Well, now I can state effective version of this result.
The statement that you think that the property equation should be true.
About zeta functions?
No, about Galois field. Or is it wrong?
Well, and Florian shares with me.
I think that concern is the Prof before. If the roots of unity are not in the base field, pth roots of, then you can't say anything. But if the pth roots of unity are in the base field, then you can describe all the decomposition roots. But you have a positive answer to this P of. And then from there, if you know the structure of the, from there you know the cyclotomic character, and there is a unique way to cover the cyclotomic, you know all the cyclotomic.
Say,
It's a very good hope.
actually, it would be enough, even if you don't assume that pth root of unity is in there. Join it, and everything is defined, and then you can come back.
No,
Well,
my problem is then when you join the pth roots of unity, that is not a p extension.
no,
It's a prime to p extension.
no, okay, say just, I don't want just to be, what is this?
Not pure property.
I don't want to be, if I need something, I can assume. Well, so this means that just not to be in the power of this statement about p extension. Okay, a little piece what is not p part, and then everything goes. Yeah. Okay, now I can start explanations. What is?
Sorry, just so is what you're saying that the only thing you need to know is that the p-adic zeta function determines the zeta function? Is that what you're saying?
Well, so it looks. So because all this statement, okay, I believe in them, and so I believe that, okay, it's justified. Well, so the relation between this, say just, okay. And this is, well, so question for specialists. Well, about effective version, well, at least if this is Galois extension. If this is not Galois extension, there are some ugly examples. Well, but actually, we are losing here also something. Okay, take a little bit from here to add, or maybe use this assumption. Well, so it's really some very tiny thing to add just to get rid of this assumption. Okay, effective version of local Grothendieck conjecture, motivation. This is Deline's interpretation. Of Krasner's lemma. It seems in the whole theory of local fields, Krasner's lemma is just the only statement what just can be used to explain everything. Well, And that was in the following form. If k and k dash are complete discrete evaluation fields, they are one-dimensional. Suppose A is natural number, then we have if algebras OK modulo pi k A plus 1 is isomorphic to O k modulo pi k dash A plus 1, then if we take quotients, these quotients are isomorphic, and this isomorphism is compatible with ramification filtration. So this means that, okay, actually working modulo some ramification subgroup. So this means just fixing the structure of local field modulo some fixed power of its maximal idea. Well, and it looks like very nice topic to start thinking if we can just go, say, in another direction to some extent. But this statement is not actually a great deal, at least for small numbers A. Say if EK is EK dash, so these are absolute ramification indices, inertia, just how they call it, degrees of residue fields also are the same. Then for any such fields, OK, say modulo pi EK is just equal because they're just truncated power series in this uniformizer, and the only difference appears if we just can't assume that P is 0. And actually it comes from a corresponding field of characteristic P. Even here, okay, one can admit that fields, just one of fields is field of characteristic P. It also states that we can't have even any hope that any segment of ramification filtration, so this is gamma k v 0 v to a, and I recall that here you have infinitely many different groups. It's just very dense and very rich. Well, so it determines only OK modulo pi k a plus 1, and we don't have chances to recover the form. So, and therefore is not strong invariant. Well, but anyway, one can say something, and theorem is the following. Suppose k dash are as earlier. Suppose there is natural number m such that zeta p to m belongs to k. Suppose that residue field is sufficiently big to log p square vk, and vk is a special constant for local fields Pm plus 1 ek divided by p minus 1, such constant. Well, and I need ak. This will be ek p minus 1 plus m. And I need, there is group isomorphism gamma k p, gamma k p ak.
I'm confused by the logic.
Yeah.
You say exist m such set, so you could tell some m and then it will be all right. What do you think?
This is primitive Pm's root of unity. I assume that, okay, this field it must contain. So
Which one?
k,
No, but which m?
some m. This statement, it depends on m.
Maybe the exist m should come outside all the bullets.
You give k palm and m and then
Suppose I have fields such that k contains primitive Pm's root of unity
yes.
for some m, for this m. And then I'm using this m
Elsewhere.
here.
And satisfies
So that-
everything what comes up.
So the exist m should be before the bullets. I think that's what he said.
Yeah. Well, but I consider this is after this. Well, yeah? They can't be treated independently. Well, yeah. Okay. So, and this goes to corresponding stuff for k dash, ak, isomorphism, which is compatible with ramification filtration. So these are conditions. So just roughly speaking, we have Pm's root of unity in K, sufficiently big residue field, and for some prescribed AK, we have isomorphism of those segments of ramification filtration.
Statement before theorem, is it theorem or it's just a heuristic reason? I mean, are you saying that OK mod pk to some power determines the Galois group and the filtration of the Galois?
Theorem
No, the statement above.
above.
So you say that the Galois group and the filtration up to ace level,
Yeah.
is it equivalent to knowing the Galois group modulo that ace level?
Not Galois group. Oh. Yeah, okay. This is sort of interpretation. Just consider this. I wanted to say that, okay, if I know only this stuff, then I know this, yeah?
Yeah, but it's
And therefore,
can be
yes, I agree. Well, but how you can use it? Well, just okay. Well, but saying you have this, and then we can do only. Maybe you can say more. Maybe. But maybe not. Okay, from this follows. Okay, it can't follow very much, but actually follows that then, okay, all invariant, they actually can be seen by first terms of this ramification filtration. But and zeta Pm is in K dash. So this is not the big stuff, so because already group structure of Galois group, it reflects this invariance. Well, and for some automorphism phi m from Galois group to P zeta m over QP over QP, there is Cm phi m linear ZP isomorphism, isomorphism of ZP algebras chi OK modulo P 1 by P minus 1 OK dash modulo P 1 by P minus 1. Well, this is statement. Well, and now well, so first of all, just remembering that OK modulo P, OK dash modulo P, they are just the same. So what's the statement? Well, but the statement is the following, that say here we consider K as absolute extension of QP. But here we know already that these both fields, they contain zeta Pm, and therefore actually now K, it contains QP zeta Pm, K dash, it contains QP of zeta Pm. Well, there is some automorphism here, and therefore this stuff, it just extends this, but it's not just something. Well, but it sends zeta Pm to another zeta Pm dash, and therefore, in other words, actually we've got the following.
So the zeta m in your statement there should be zeta p. At the top, second line.
Oh, yeah. Thanks. Well, and so in other words, under suitable identification, say identify K is K dash, pi K is pi K. Okay. Choose suitable this and suitable this. Well, and after this, zeta Pm and some other zeta Pm as element of K, this is as element of K dash, they have same truncated expansions in pi K and respectively pi K dash modulo P1 P minus 1. And here, under some assumption, actually this allows us to reconstruct these fields K and K dash as extensions of Q of zeta Pm. So just making first it's not precise. If K and K dash are not very much ramified over QP of zeta Pm, then they will be just isomorphic. What it means to be not very much ramified, I will give you just the last interpretation of this. The simplest interpretation, or maybe the both. So to be not very much ramified, in this context, this means the following. If you consider Galois group K over QP zeta PM, if you consider here upper ramification subgroup with number Pm minus 1, it must be 1. And actually, how to make it more simple? It holds if K is composite K1 and QP of zeta P2M, where ramification subgroup of QP with number m minus 1 acts trivially on K1. So this explains the role of this M. Suppose I want to recover, okay, maybe not my field, but okay, something when we join this root of unity, just about that procedure of joining something what we need. Well, so in this case, we do the following. Take the first, which acts trivially on K1, join corresponding Pm's root of unity, and then for this field will be uniquely determined by the segment of ramification filtration of length, oh, it disappeared, of length AK. AK was given by that formula. Well, so this is how it looks. Maybe a couple of words, general words, because, well, so the technique is completely different, but nevertheless, okay, still just thinking about this. So I hope that one can come back and make it more interesting, that Neukirch's statement, and the possibility to think about the same local statement in the context of higher local fields, also to go from the other side to that Florence theorem that finitely generated field is determined by its Galois group. Say to come from this, from local point of view. Well, so I have no idea how one can just apply these local arguments in the context of really algebraic geometry when you speak about curves. Well, but anyway, so still there are some interesting problems to study. Well, and it's essential that technique here is completely different. Say, what is this technique is based on? Well, so first of all, I need explicit description of ramification filtration, not modular something, so just modular third commutators. Well, so and this can be done because, and that was even possible to do only because I was able to identify part of Galois group modular third commutators with some Lie algebra, not on the level of abelian quotients. Say, for example, if you want to work modular third commutators, you must specify elements of Galois group. They are never done in an explicit way. They just exist somewhere. And in order to make difference between two lifts of the same element from class field theory, you need to do something. And that appears as that nilpotent version of Witthardt-Schreier theory. And based on this, actually, there was some tricky calculation. Okay, but it worked, and this gave these generators as elements of Lie algebra. Sufficiently symmetric, though calculations were hard, but okay. That was clear for some arguments that it should be this way, but then it happened to be a very long story when I managed finally to prove this. And after this, we just apply this to this problem on the level of fields of characteristic P. Going to characteristic 0, this is the field of norms functor. Okay, in one-dimensional case, it's given by Fontaine and Winterberger paper. In the case of higher local fields, well, so that was developed, just developed. Actually, there are three approaches to this construction of the field of norms functor. One belongs to Andreatta, and Avita is using this. They're using this together for something complicated for algebraic geometry. Then Tony Scholl did it in the simplest possible terms, and this really works very well. But his construction is not done purely in terms of ramification theory. And my construction that was adjusted especially for this problem, I need just infinite series of extensions which are given precisely in terms of that ramification theory. And therefore, if we have isomorphism of Galois groups which corresponds to ramification filtration, and therefore one infinite sequence of extensions, it goes to infinite sequence of extensions which have similar properties, and therefore we can take this for the field of norms, and therefore we have corresponding map of Galois groups on the level of fields of characteristic P. We can use this explicit description, and then after deducing very strong restrictions there, just it's a technical thing to come back to on the level of original fields. Effective version also is based on something, but here the field of norms functor is applied in a little bit different way, not standard way, what was earlier. Now it's more or less standard thing. If you make this infinite extension with not Galois, but join pth roots of uniformizing elements. This is not Galois, but actually 15 years ago, I just first used that idea for explicit Bruckner-Vostokov formula for the Hilbert symbol, and this works also very well for this effective version. So just modular all those details what I had planned just to do a little bit more special. But this is time to stop now.
So you understand well that you understand the field of norm from class field theory, the multiplicative group, but then you need to define an addition also in some way.
Excuse me?
I don't understand at all how the fields of norm come in. I understand that class field theory can give its multiplicative group, but where the addition will come from?
No, but actually class field theory, one can avoid using of class field theory when constructing this theory of field of norms. Actually, we need, okay, it's very close to all that you approach when you were working essentially with that Fontaine's ring in that your paper, just about comparing characteristic P and characteristic 0. Say in the case of high-dimensional local fields, I'm just working with sequences, say, of elements alpha n, such that alpha n plus 1 to p is congruent to alpha 1, just modulo something fixed. And after this, just one can organize this procedure in that way that ramification theories, they also correspond one to another. Say, if you start with some map of Galois groups, which is compatible with ramification filtration for fields of characteristic 0, then you go up, and then you have map of Galois groups, which is again compatible with ramification filtration, and everything can be proved. And actually, that my construction of high-dimensional version of this, again, Krasner's lemma. This is just the main tool. Okay, it's stated in a little bit more tricky way, but okay, anyway, this is just the same idea.
But class field theory, you know the principal units. You know the multiplication by them because that's a group law. Now, if you take the log of that, you discover the addition. But now you need the multiplication on this thing. And that is, where from do you get the multiplication?
It's okay. You are still under influence of that Mushitsuki's approach. He goes in this way. His paper only 5 pages, but it essentially uses all ideas of periodic Hodge-state theory. And he recovers this, okay, after taking log, he recovers actually the whole structure. He has one field and another. And he makes Lubin-Tate groups which are related to these field extensions. And then on the level of some part of these Lubin-Tate groups, he has isomorphism, and it's given just via that logarithm. And from this, it follows that both operations which are encoded in that Lubin-Tate group, they coincide. It's a very interesting thing, and well, so, but okay, I'm not surprised because it works in much more general setting. Well,
So
but
the point is you do not do something similar.
okay, I repeat. Okay, in the case of fields of characteristic P, I have maybe a couple of words. Yeah? Some people used to finish even well. So okay, just if I try to explain how it goes. Say for fields of characteristic P, and this is enough, yeah, okay? Well, in this case, so first of all, I have identification, okay, characteristic of K is P, yeah? I have identification, gamma K of P, modular subgroup of P's commutatus with L modular its ideal of P's commutatus, where L is free ZP Lie algebra. And the composition law, what is taken, is induced by Campbell-Hausdorff formula. So composition law is Campbell-Hausdorff formula. It contains denominators, but they appear only on the level of P's commutatus, and so this gives actually this restriction. This actually, well, so it's not a good idea to apply somewhere this Campbell-Hausdorff formula. It's so inexplicit. But that was, I tried to get rid of this, but it used to come again, and finally, okay, I had to accept this. Well, well, after this, I'm using extension of scalars here, and this is why this theory, well, so okay. I can't make these operations on the level of groups, but on the level of Lie algebras, just what we can make, this extension of scalars, and then it has a natural basis. It appears by elements DAN, where A is prime to P, as usually in Artin-Schreier theory, as we have these elements. All coefficients, they actually are encoded in this. And say, if I put here n any integer, I'm using this is actually integer is defined modulo n naught, where k is fp n naught. Well, it doesn't matter. There is some procedure of identification. It depends only on the choice of uniformizing element. And here, it would be nice to get rid of this because this would have given nilpotent class field theory, what again I am dreaming about, just to use this construction in here. If you have this nice identification, what modulo second commutatus, this appears as actually identification of class field theory. Modulo of generators here, this is actually P completion of K star. And if
you are looking at the abelian curve.
first of all, I have I can introduce Lie algebra. which is freely algebra, ZP, with generating module P completion of multiplicative group. Yeah? Okay, say, and then I claim that after choosing uniformizing element in here, I have natural identification of these two objects. Well, say, and then if I produce here modular second commutators, this is maximal abelian quotient, this is this, and this arrow, it's essentially, as a fact, this is class field theory map. Okay. After this, in order to get natural system of generators here, I have to extend scalars, and then I have here natural system of generators, where A in say natural number, which is prime to P, it corresponds to Artin-Schreier equations in this way. This problem about alpha, this is already resolved by introducing this and is assuming that there is n what is actually depends modulo n. Okay, now we have the situation where we can forget about this. We have this Lie algebra. Well, after this, I can find ideals which correspond to ramification filtration. And say essential, I will give you only one formula. There are special elements F gamma, where gamma is actually rational number, which are given in this way. If gamma is not integer, then this gamma is -1/2 sum A1 Pn1 d A1 n1 d A2 n2. Okay, modulo C3, where n1 n2 and A1 Pn1 A2 Pn2 is gamma, such that LV W of k is the minimal ideal containing all sigma n f gamma bigger or equal than v. Okay, I didn't specify if gamma is n, there will be just linear term here on the same form. Well, sigma n, so because I made extension of scalars, all ZP modules are becoming W of k modules, but action sigma, this is natural on coefficient n goes to n plus 1. So these are, well, so it's easy to treat these elements. After this, suppose I have automorphism of this Lie algebra, which is compatible with ramification filtration. What's interesting, okay, it seems automorphism must be done by some formula, but because essentially only commutators, they will play a role, it's sufficient, say, dA0 goes sum alpha ABM dBM. If I apply sigma here, sigma must be applied here. And okay, the question is about finding conditions for this stuff. But then I know that automorphism of field K, they do the following with this field K. These are just analytic automorphisms. I can always apply analytic automorphism here just to normalize the situation. So this normalization can be done. I can always make this to be all alpha 1 1 0 can be assumed to be 1, because I can always map t to some multiple of t. Then alpha 1 b 0 can be assumed 0 if b is greater than 1. Any b what appears here, this is prime to p. And because actually 1p, it doesn't exist here, but it exists as analytic automorphism. I can also add to assume alpha 2 b0 is 0 if b is 1 modulo p. Well, I can assume this 1, 2, 3. After this, I'm looking at this formula. I try to adjust this stuff, and I prove that all others are 0. So this means I never care what's multiplication, what is addition. This means that, okay, this condition to be compatible, this means then after applying analytic automorphism, I can reduce this to identity map. Well, so that was the idea of it worked.